Okay, so what we have is a whole bunch of expressions. And if you identify all these expressions and what they're related to and understand what they're related to and how they came up in lab and in the problems that you solve for homework and so forth, then you're probably in fairly good shape. Okay. And if you don't, well, see if you can get there. I'm going to talk about it. Okay, first of all, how many understand what that is? Just give me a thumbs up, thumbs down, or to the side.
Elevating a dish by having things that.
That's your universal law of gravitation. Universal gravitation. Universal, I'll abbreviate it so you don't know whether it's gravitation or gravy, but there it is, okay? And to complete this, we complete it this way and go back to the explanation you see in your text, go back to whatever you see in videos, use AI to search it and explain it to you, but make sure you understand it. Okay. Very easy to use. And then it leads to other things like your definition of potential energy and stuff like that. But we'll talk about that when we get to it. If we do, let's see, is it on here somewhere? Yeah. And what's this? How many of you know what that is? Know it, not sure, don't know. A little clearer now.
Democratic process of voting, but it only works if you know. So I guess you ever look at let's start with this. The article for the midterm. It has a few new submissions for final. So again, for our, we will have a
Starting off small, can't even read that, but omega's a square root of k over m. I don't even need that because I already told you what it is. But that's what it's related to. There's a differential equation. Everybody who's taken differential equations knows how to solve this equation. Get your characteristic equation, solve it. And if you don't know differential equations, you know that you can substitute this into here and it gives you an identity. Okay? As long as omega equals the square root of k over m. So make sure you understand that. This one, well, I kind of screwed up. That's meaningless. Not much meaning. Now, let's see if I've got any others.
There's what we're just talking about, right?
Wait a minute, what am I doing?
What kind of crops are they growing?
I don't know why I said that. Okay. Integral of a dt.
I have to say,
dv dt equals a, right?
you don't really see.
Integral of a dt.
vertical length back there, there's gonna be their hydroponic setup.
Anti-derivative is just AT plus C if you assume A is constant.
Something you really want to work under. So modern LEDs are kind of like lifestyle. Right. We'll dive that. I wouldn't bring you back. We're gonna see,
We can say that. We can also say
and those
it's the integral T1 to T2 A of T dt equals B of T2 minus B of T1. So if you want your change in velocity and your acceleration happens to be a function of time, you get that. You need to understand that in terms of Riemann sums, in terms of everything you learn in calculus. Okay?
mostly growing potatoes.
Now, what's the integral of F dot ds? How many of you did that? Okay, this is a work.
Here that said they're not really using it in the industry, but here they are using it as you go on environment ever.
IF through this infinitesimal displacement vector ds. Now that comes from the fact that if you have a force and a displacement, the work done is equal to the component of the force in that direction. We'll call that F parallel. And the work is F parallel times delta S. Very fundamental. Scan through the book on force and work. You should really pretty much try to scan the chapters of your book and pull out things that are unfamiliar to you or things that you think you're not going to need and ignore, or things that you think you're going to need so you can go back and note them a little more. Maybe start with the chapter summaries. One way or another, try to get the picture of the whole course in your head. But that's a fundamental definition right there. It's just fundamental to everything we did with work and energy. Okay. What's this? Just give me thumbs.
Solar to take away.
Well, this is impulse.
But yeah, so there are.
Now, J would be the impulse of the force with respect to T between two times, between time T1 and T2. That would be the impulse. And if the only time a force occurs is between T1 and T2, then that's the total impulse and it equals a change in momentum. And this is very fundamental. Okay. So these definitions extend to angular quantities. And I haven't included a whole lot of the angular quantities here, so let's just make a little note. It also
I have not used AI. Listen, things like. Do you have any AI manipulators like? Yeah, I use a lot. It's like it messed up a lot, right? So I'm curious.
integrate the torque dotted with your position increment, your displacement, your infinitesimal displacement, you get the work done by the torque through that displacement. And if you integrate that, then you get the work done by tau between two thetas. So we could say theta 1, theta 2. That's work done by tau.
They're looking here, mostly seems to be from like a growers perspective, how they're talking about how other growers.
Between theta equals theta 1 and theta 2, you can make analogous specific statements here. Okay, this integral from position 1 to position 2 of f dot ds is a work done by the force half and so forth. Okay. There's more I could say in here. But it comes up later. Okay. What's R cross F?
Google has like that now, anytime you do a search, it's like, here's your AI overview, it's like,
Equals a torque. So it's like you've got, here's a picture, you know, draw a little picture there. You got a beam maybe rotating about this point, and you apply force. Now, most of the time when we've done the rotating beam, the force has been perpendicular to the beam. This force isn't perpendicular to the beam. There's your force. Here's your R vector. And
Let's see.
the magnitude is the magnitude of R. And by writing R without the arrow over it, I'm talking about the magnitude, right? Times the magnitude of F times the sine of theta.
So it's interesting, like, to look at it under the hood a little bit, and you're getting that information, you know, it's drawing a lot of information.
So you can do an expanded picture of that, draw your own picture. Make sure you understand
so,
it.
like, looking at search engine, I think what that article was saying is like, you really want to have your like metadata, the stuff that.
What's this?
Kind of behind the scenes, your searchable information, like you need to have those keywords up top. So
Okay, most of you have your thumbs up or you're writing something with it. That's okay. Okay, I'm going to assume people are pretty good with that. It's pretty something we've done quite a bit with. This is angular momentum.
Say how about all three? Find that survey.
And you can put an arrow over that omega.
Okay, we got
So we can call that L. It's angular momentum.
Liberty Foundation. Really, just all three. I don't know how I feel about that. Have you seen one on here?
Change in angular momentum over an interval, and I'm not going to write out limits there, but you can make it more specific. Is the integral of torque with respect to time. This is angular impulse. Actually, I don't know why we wrote delta L.
they do supply the plants, but they're usually not.
The reason I wrote delta L is that it is delta L.
And you get wholesale plants, but, we tried them one year, and it's not.
I think I had delta L there. As I was looking at it, as I said, L was equal to this. That's not our symbol for angular momentum. So just to say delta L, change in angular momentum is the integral of the torque with respect to time. And this integral,
But, finally,
this is angular momentum.
hearing about.
Um,
Those recent winners, that familiar with recent winners? Winner is like.
integral here is your angular impulse. Angular impulse equals change in angular momentum. And be careful of right-hand rule if you got a situation that involves this thing. Okay.
And that's being a great example of hybridization of native for create a more suitable landscape plan. With New York iron, we kind of discrete
Okay.
native species getting over.
Now, what about kinetic energy?
And the new hybrid being shorter.
Well, everybody knows that this is
They're familiar
1/2 mv squared. And it's equal to an integral
I mean, 2026, prairie princess iron.
of the net force through whatever displacement. Well, we've already seen that integral, but I didn't have a net on this one. This is just the work done by whatever your force is. For example, if you're trying to push a car up a hill, okay, the work you do is not equal to the change in kinetic energy.
Looking at.
Because you also got road friction, which is dissipative, and gravity, which means your potential energy is increasing. So your work's going into overcoming non-conservative forces and increasing your potential energy. Okay. That's worth understanding. Had a good perspective. I think most of you understand that. To greater or lesser extent, but you want to be sure you have complete command of it. So this is the work you do, and this is why you get out of breath
There's a lot of them out there really for this.
or get tired. Okay,
The native or.
or fall down and the car runs over you, go back downhill. Don't do that.
And.
Okay.
Hybrid, right, so.
At least get between the wheels and not under them. Well, anyhow. There we have this,
Do you have a?
which is
Let me see this USP. That is.
work done by the net force.
Plant
Um,
which, what does that mean for us?
delta K. Now I used KE as opposed to just K because there are a lot of K's floating around. You can't tell whether that's a capital K or a lowercase k or a kappa. So I put KE, but now in this context, we generally use just plain old K when expressing the work energy theorem. Okay, that's your work energy theorem. Now your conservation of energy theorem goes a little further, breaks W net into the work done by the conservative and non-conservative forces. It gives you the general conservation of energy equation. Okay, it's an idea though. About the idea, not just an equation. Okay, how about 1/2 kx squared? Okay, people are saying, pretty familiar with that. We've been looking at it recently.
Some people are like strongly.
Right, it's an integral. It's the integral of kx dx.
Thumbs down. Get a couple thumbs up.
I'm going to say it's the negative integral
Most people are kind of maybe on the neutral
of negative
side, right?
kx dx,
I think it's
which is
one of those things where I think we need to know about it, right? We don't want to violate it. However, I will say that,
your elastic potential energy. The integral of negative kx dx is the work done by force equal to negative kx. Negative kx is your spring force or your elastic force, whatever, in the ideal case. In the ideal case, that would be the net force. This is a conservative force. It's path independent. It doesn't reverse path when you reverse direction. If the spring's pulling back on you here, it doesn't matter if you're passing this point here in this direction or this direction. The spring, at least an ideal spring, is exerting the same force on you, unlike friction, which exerts a force in one direction if you're going this way and in the opposite direction if you're going this way. Make sure we understand conservative forces. It's very important, very, very important concept to understand. Okay. What do you think about F cosine theta? Might not be clear what in the world I'm talking about with F cosine theta because it could arise in different cases. So what I have in mind here is just a picture. The force F. So it's the x component of your force, provided theta is measured from the positive x-axis counterclockwise. Energy and water management. Theta a little bit, okay. And of course, you'd have F sine theta, bigger projection in the y direction on the y-axis. What can you tell me about the cosine of omega t? Yeah, don't tell me because we got the camera on. Okay, well, it depends on the context, but omega t appears to relate to something rotating in a circle, rotating through some angle. And it could be an angular frequency, right? But the picture you want to get with cosine of omega t is a unit circle. And omega t well, let's say theta equals omega t. So you're right at this point. And x equals the cosine of omega t just by the unit circle definition of the cosine, right? Make sense? You really have to have that picture. It's a picture you should have had in your mind ever since you encountered the circular definition of the sine and cosine and tangent. Okay? It's fundamental. So if that picture isn't firmly in your brain, could be because in your trigonometry class you knew you weren't going to be tested on it, so you ignored it. Could be you didn't have enough problems that caused you to think about this. Could be you were just zoned out when that came along. Okay. Those things happen. But don't go through the rest of your life without knowing this very well. Okay? It's fundamental. Trigonometry is fundamental. And the circular definition is fundamental. Got a question? Okay, so the question was, does this have a name? Well, personally, I call it Joe Bob, but most people call it the circular definition of the trigonometric functions. And I'll abbreviate that.
And, you know, to sharing with the elders. And this is your first on here, and you can tell us about it.
Circular definition. You'll never understand simple harmonic motion very well if you don't know how to relate it to the circular definition. So be sure you do. It's about as fundamental as 2 + 2 = 4. Okay. So pay attention to it whenever it comes up. Okay. What about this integral f of r dr? Well, the context would be the work by f of r from r1 to r2. If there's a condition on this, provided f of r is parallel to the radial vector.
And yeah, I totally agree. It's a little test, right? I get it every year.
So I'll just say if f is along the r axis.
Questions for Hannah about Wilbur Tilson. It's a solid, strong name right there.
The paradigm example would be you have a planet and a satellite. And here's your r axis. It's bad looking. I wrote this, make it a little more woody. And you're at some point on the r axis. And typically, f is big G, big M, little m over r squared. Negative. And that's the same as the universal gravitational formula. If you just ignore the unit vector. Since the force is along the radial line, you don't need the unit vector. Okay. Now, most of you are going to be taking multivariable calculus. If you're not moving parallel to the radial vector, then you're going to have to do an f dot delta s, an f dot ds. Okay. Turns out that the only thing that matters for gravitation, the work done by the gravitational force or the change in potential energy, okay, which is equal and opposite to the work done by the gravitational force. The only thing that matters is how far you are when you start and how far you are when you end. Doesn't matter what path you take. Because the gravitational force is conservative, it's path independent. Now you're going to see a lot about that in monotopic calculus, but that's your definition of a conservative force. It's path independent. So if you're out there moving around in space, you want to see how much energy it takes to get from this point to that point. Just ask yourself, well, if I went in a straight line from here to that, from this distance to that distance, how much work would I have to do? Okay. Now, of course, you're out there in space and you just try to go straight. Well, you got all kinds of problems with that. Very counterintuitive. Anybody ever driven around in space? You got to try it someday. Okay. It's really counterintuitive. Get a good simulation. It'll drive you nuts. Okay, well. About F net equals mx double prime. Everybody recognize that? It's the most foundational thing in the whole course. Maybe.
Commonly used, especially in and rather than like the term original completely often through kind of
Newton's second law.
Yeah, I like that.
X double prime is acceleration. It's force equals mass times acceleration. And that got used right here. Make sure you understand this in the context of this. Incidentally, I said something wrong the other day about the thing you did with the two chains on the rotating beam. I said that when you have a drag force, it changes the period of the motion. That came out clearly from your data. Okay. Well, what I should have said is if you have a linear drag force, which is what you've probably understood, probably dealt with if you're in differential equations. You probably haven't dealt much with nonlinear drag forces. Okay. Linear drag forces just go into your characteristic equation and everything comes out. Nonlinear drag forces will change the period. The lesson is that something was going on in that system that was nonlinear. There were nonlinear forces involved. The force was not independent of probably velocity. It wasn't moving very fast. I don't think air resistance was to blame. I think it was probably a nonlinear friction. It depends on velocity. So take that for what it's worth. You're not going to be tested on it. It's just kind of something. If you get into mechanical engineering, you're going to need to understand those things. And just giving you a little head start. Just raising the question. Anybody wants to analyze it, we can. Okay, what about mg sine theta? That's something you've probably seen a lot of. That's just the component of gravitational force on an incline. If you set up your coordinate system correctly, or in the most advantageous, there are all kinds of ways to set up your coordinate system. Like you got this, you got mg. Theta is this angle here. So that this angle is also theta.
So I'll say I did.
So that the projection of the force on the mass, the projection of mg on the mass is mg sine theta. I've also got mg cosine theta, which is going to be balanced by your normal force if there are no other forces involved. Okay. And you also got friction, which is proportional to normal force and all that stuff. So you really have to understand that picture. Very good chance you're going to have to go out and explain it. When I say very good, at least a 40% chance. Okay.
And heavy metal was the worst.
One of the more important things. Okay. What do I mean by delta P? Okay. Change of momentum, right? I'm running out of room here.
So yeah, there's something to that. Sound waves, which affecting time growth. I think there's a lot of work that goes with that.
I got this change in mom with a period after it. It stands for momentum, not a maternal parent. And change in momentum equal to impulse. Of your net force. Had to write that really small. It says equal impulse of F net. Okay. So you could say J, which is a symbol your text uses for impulse, right? Am I right about that? I've seen different symbols for impulse. And I use J down here also. And that is, of course, you have to understand that impulse is basically the force times the time interval. But usually it's a variable force, like in a collision, the force starts at zero, then the two objects start interacting and the force increases, and then they push each other off and the force decreases. Okay, so you have to do an integral. Usually, or often, the Gauss, an e to the x squared type, e to the negative x squared type force, L shape. Okay, frequently. Okay. What's delta P1 plus delta P2? And why is it equal to 0? And I can put arrows over this. Incidentally, as soon as there are arrows over these things, it applies to the X component, it applies to the Y components, and it applies to the Z components. Every component satisfies this independently of the others. Okay? That's a real important idea. Okay? So, and if these are vectors, the zero better be the zero vector. Okay. So some of these equal to 0 means it's momentum conservation in an isolated system, because in an isolated system, there are no external forces. The only forces, if it's a collision, are between the two objects. There's nothing outside putting a force on it. Now, if I collide a couple of blocks that are sliding across tabletop, well, there are external forces. There's a frictional force. Okay, external to the two blocks, to the system of two blocks. So you have to take the tabletop and all the energy dissipation due to the heat and all that stuff into account. And it gets really complicated. If you want to just talk about an isolated collision of two or more objects, or an isolated interaction, you have this, okay? Isolated system means no external forces. Okay. What about delta K plus delta U? What's that equal to? Somebody can tell me. So work done by non-conservative forces. Now, several times I've gone through the idea and developed it, including in the last class, that you combine the fact that the work done by the net force is a change in kinetic energy. The work done by the net force is the work done by the conservative force plus the work done by the non-conservative force. The work done by the non-conservative force is equal and opposite to your change in potential energy. And this follows immediately, and you really want to make that connect. You really want to understand that. Now, if you go to the video from last time, I'm pretty sure I put that whole set of reasoning into the description of the video. The description's a couple hundred words long, something like that. It's worth looking at. It's worth making sure you understand every detail. Okay? Because it's very simple. I mean, here you got W net. That's W conservative plus W non-conservative. W conservative is negative delta U. So delta K is negative delta U plus WMC. Take the negative W, move it over here, and you add it to delta K, and you get this. Now, you not only need to know that that's true and why it's true, you need to be able to apply it. And this is maybe the biggest of the biggies. Conservation.
So it's actually good for nitrogen using
Of energy. Fundamental. Most everything. Where's my red chalk? Obviously, I've got it in the container with the blue M, so I can't ever identify it.
Point beans squashed together. Corner for the beans fly.
Okay, what about W net?
Classic intercropping foundation. Cool.
Well, that's just the work done by the net force.
I think you all sharing your business from all of the elders. Session one will remain open. So if you get anything in, before next Monday, we will.
It's also equal to
We got a lot of good business, so come back.
work done by the non-conservative force plus the work done by the conservative force, since you assume that your force is a combination of conservative and non-conservative forces. Okay? Now, some forces like rubber band forces, you know, the whole conservative, non-conservative gets mixed together in the way the polymers slide across each other and so forth. But you can still measure how much potential energy changes, how much of your energy is lost to non-conservative forces. What about V squared over R? Okay. It's centripetal acceleration. Picture goes with that. Is you have your two positions. So you have your change in position. I did this in class. Advised you to be sure you understand where it comes from. Right there is your change in position. You could call this vector R1. It's badly, the chocolate behaved. My hand didn't make it behave. But you got R1 and R2. That's what those incomprehensible symbols are in this tiny diagram with two R vectors for an object moving in a circle. Okay. So your displacement is delta R. Well, it goes, I don't have room to get it on the board. Look it up. Y is centripetal acceleration equal V squared over R. Just high school trigonometry. Okay. Very simple. Comes down to this. You got a V1 here, V2 here. So you draw V1 here and V2 here. I mean, they're not really here, but they're vectors. They can go anywhere. And you got your delta V. And your delta V over your delta T is your centripetal acceleration. And don't have room to do the details. I'm not just going to recite it. Okay. Over your head. At this point, look it up. Okay. What about V naught sine theta? Where do you see that? I mean, you see it in a lot of places, but it's a vertical component of your projectile motion. Okay. Or your initial projectile motion. I mean, an expression like this can appear in lots of places. It's the y component of V naught, right? And in a projectile, you have a V naught, and that gives rise to a projectile motion. And for a projectile, Your premises are X, one of your acceleration is 0 for an ideal projectile, where you can ignore air resistance, and A sub y equals negative G. Those are your premises, you set up your equations, and you solve the problem. Very high likelihood you're going to see one on the exam. Okay. Now, MR squared. Okay. Well, moment of inertia of a point mass. Now, there are many more qualifications. You know, R is going to be your distance from the axis of rotation. Okay.
Okay. Made you attracted to the thing.
Point mass M, R is your distance from the axis. Then
It is native here, right? Yeah, Americana, so.
I is the sum of all your MR squares.
Actually,
Okay.
my mom's twin, her, that's probably the first number I got, right? She will always take pictures of things that she doesn't know, and put one of them.
Which is the integral of MR squared dr.
Boil down to water boiling, but I didn't.
And look at how moment of inertia of the disk, of course, there is found by integration. Go back to the problem that you did. Everybody seems to have done it right. For homework, we had to integrate to find the moment of inertia of a beam about a certain point. Okay, integrate from x1 to x2 and all that stuff, and take into account the density. Okay, what's this? I'm not seeing a lot of things down either, but must be somewhat unsure. You really can't be unsure of this. It's got to be second nature. So make sure it is. Gravitational potential energy relative to infinity. And we've done quite a bit with that recently. Okay. What about this thing? That's what I mean by net force. Add up all the forces. Okay. And you could put, from I equals 1, and you have discrete forces. And that breaks down into the sum of the X forces, the sum of the Y forces, the sum of the Z forces. So in an equilibrium position, F net is a zero vector. Sum of your X forces equals the sum of your Y forces equals the sum of your Z forces, which is 0, which is the same as saying that the vector, the net vector force is 0. Only way a vector can be 0 is if all three of its components are 0. That's your equilibrium condition. And also you have.
So it's being used in studies to help smokers quit. A long time ago, it describes use of flowers and leaves in the tea of alleviating stomach cramps. And actually, Pawnee tribes would use the flowers in the love concoction as well. The red part of the
So
flowers
equilibrium says that the sum says that your F net is 0, which comes down to the sum of the X, Y's, and Z's is 0. Also,
It's such a cool plant with a lot of interesting
the
qualities.
torque is 0.
Purple flower. It's beautiful.
It was 1/2 GT squared.
At party. Like it is a hardy perennial, but it doesn't come back every year. I don't know why. It's hardy. We got questions for Ali about the Cardinellus, the cardinal flower.
We could say Y equals 1/2 GT squared.
Yeah. Overly say is how they manage to say the structure are very similar to nicotine. So it's this thing that nicotine is sensitive. And it was used for sedation a long time ago. And then there are some theories.
So it's free fall if your velocity and your position are both 0 and T equals 0. And we would put a negative on it since Y is kind of by default upward.
Some people think anyway.
And just a second. Well, you integrate G, which is your acceleration, and you get your velocity, right? And you integrate your velocity and get your position function. So that invokes everything that's kind of implied by this. You start by integrating A with respect to T. And that is V of T. You integrate V with respect to T and you get your position function. Fundamental. And, you know, in some ways, that's even more fundamental than conservation of energy, although conservation of energy is much more powerful.
Any kind of outliers try to.
So is conservation of angular momentum. I mean, all these things are really good. This is just because velocity is rate of change of acceleration, and acceleration is rate of change. I mean, acceleration is rate of change of velocity. Velocity is rate of change of position, right? Let me write that down because it's really where everything starts. First thing we did.
Now you added this. We'll have a category on now you added.
Acceleration, rate of change of V. Velocity is rate of change of X, which is your position. Or in general, velocity is the rate of change of your R vector. And that's the way we're going to treat it early in molecular calculus.
Identify all resources and serve as inputs to the production service.
Sum of F sub X.
Supply by demand. Well, because, yeah, it's ideal, but something's hard. How hard your service, you know,
Again, it's going to be hard to read, but it's a net force in the X direction. There's no real ambiguity. I've already kind of talked about that down here. It just fits into this scheme. Okay. So if you want your acceleration in the x direction, you add up all your forces in the x direction and divide by the mass. What about the square root of big G big M over R? Know what that means? Know where it comes from?
People profit plans, kind of what they look at, even though they look at the dimensions of not just economic, but environmental. So following are the physical aspects of marketing of all verticals for products and services. The product don't have a result.
Everybody did it in class and did it right. Very simple. Write down the expression for your gravitational force. Write down the expression for centripetal force, which is mass times centripetal acceleration. Just put an M in front of it. That's right. And solve for V. 2 steps. Everybody found the algebra very easy, which is good. Okay. I'm never quite sure when I pose that thing to a class. Everybody's algebra is up to it, although if you're a second-year engineering student, almost certainly you'd have died if your algebra hadn't been up to it. Okay? You'd have never performed very well in your engineering classes. So I think you tend to have, and if you had a year of calculus, whether you're an engineer or not, your algebra is going to be up to that. And it was. I didn't see anybody who couldn't do that algebra. So I'm not going to talk anything about the algebra. What about the square root of 2k over m? Well,
so in some ways we can consider it, it's marketing.
Kinetic energy is 1/2 mv squared. You solve for V, and you get V. That's not something you have to memorize. This is baggage if you feel like you have to memorize that formula, okay? Because you know that kinetic energy is 1/2 mv squared. So if you give the kinetic energy and the mass, you can find the velocity. So you just write out this equation and solve for V. You don't really need this. Sometimes it's handy to have, but you can always derive it. I mean, nobody had any trouble doing the algebra for this. The algebra for this is almost trivial, right? You don't need to memorize 50 formulas if you know how to use a few that you really do need and recognize how they're related and what they mean. Okay, I guess I thought I had another one down there, but that was just writing that I did for something else. Okay, so I started with a nice, neat board, and I just totally messed it up with all these details, but that's kind of the way physics is. You get all messed up by the detail, and you don't see the forest for the trees. So what we started out with was the trees, and then we just grew a big old forest around. But the idea is to help you sort through that forest so you see the main points, okay? So that's about it for the semester. Final exam will be in the testing center next week, all week. Okay, probably not till Monday afternoon unless somebody tells me they want to take it early on Monday, in which case I can email a copy and go print one. Okay. So if you do want to take it before Monday afternoon, let me know. Very easy for me to handle that, but I don't want to bother the testing center staff with an email, but I can put the thing off and get it over there in the afternoon, okay?
But it's been a pleasure having you guys.
However, if you want to take the test in the morning, I don't mind bothering them. They don't mind being bothered. Very good. Okay. Okay, well,
Yes, have a great rest of the week. See you
good
next
luck with the exam. I'll send out some sample problems.
week.
Okay. I'd hope to have those ready today, but there are just too many things going on this week. 2 weeks ago, time I lost. I just don't have it ready yet, but it'll be coming out at the latest by sometime tomorrow. But hopefully later on today. Okay. Let me know if you have questions. Good luck. Review as you find appropriate.
Thank you.
And
If there's not a-
hopefully we'll get some good results.
But, uh,
If everybody does well. Okay, any questions? Let me go ahead and stop the video. If we don't have any questions, that'll be it.